First, I would like to thank the organizers for giving me this opportunity to present my recent work. I will talk about thermodynamics of entanglement entropy for excited states in some non-conformal background. This work is still ongoing, so your comments and suggestions are welcome. This is the outline. Section 1 gives you a brief introduction. The first part is a review of the first law-like relation for holographic entanglement entropy derived by Takayamagi's group. And the second part of section 1 tells you some fundamental backgrounds of non-conformal DP branes. In section 2, I will present the main result, that is the entanglement temperature. As a warm-up, first I obtain the entanglement temperature in 10-dimensional space-time. In order to show that the behavior of the entanglement temperature is independent of the frame, I consider the P plus 2-dimensional effective theory and consider two different cases, the strip and the sphere. Finally, section 3 gives a brief summary and discussion. Okay, let me start with the motivation. We all know that the first law of thermodynamics, I think everyone knows, it tells us how the entropy changes as the total energy of the system is increased. Since the entropy counts the number of microstates of the system, therefore we can say the first law of thermodynamics is a fundamental law which relates the information of a system on the right-hand side to the total energy on the left-hand side. In quantum many-body physics, a good candidate for measuring the information of a system is the entanglement entropy. The previous speakers have already made excellent reviews on this topic, so I will be in brief. Let's consider a system and divide it into A and B. B is the complement of A. The entanglement entropy is given by the so-called von Neumann entropy. Here, rho A is the reduced density matrix. That is, we start from the total density matrix of the system, and we trace out the contribution from the complement. And then we apply this formula. This is the calculation from the field theory side. And the entanglement entropy measures how a given quantum system is entangled. In 2006, Yu and Takayamagi showed that the entanglement entropy can be calculated via holography. That is the so-called holographic entanglement entropy. Now, this is the Yu-Takayamagi formula. Consider static spacetime, and in the larger limit, that is the bulk gravity theory is described by Einstein gravity. The holographic entanglement entropy of a subsystem A is given by the area of gamma A divided by 4 times the Newton's constant. Here, gamma A is the minimal surface whose boundary coincides with the boundary of the subsystem A. We can say that entanglement entropy is also one kind of entropy. So we may ask, is there an analogous relation for holographic entanglement entropy? The answer is yes, which was shown by Takayamagi's group in last December. This is the first law-like relation. The left-hand side denotes the energy of the excited states. And on the right-hand side, we have the correction to the entanglement entropy. This quantity is defined as the entanglement temperature. Their derivation is based on asymptotically ADS spacetimes. We can write down the metric. Yeah, here R denotes the ADS radius. And we have non-trivial functions f and g. Indeed, we are dealing with static spacetime, so GTT is not so relevant. But GZ has some relation with f. The asymptotic behavior of GZ is given by this expression. As v tends to the boundary, z tends to 0. In their derivation, they do not need to make any assumption about the IR region, that is, z tends to infinity. In the IR, we can have either black brains, which describe thermal states, or stars, which describe zero temperature states in the IR. So this derivation is very general. Now we have the background, and we could calculate the both sides of the first law-like relation. How to evaluate the correction to the entanglement entropy? There are 3 steps. First, we work out the extremal surface gamma A for the ground state metric. That is, we can simply put m equals to 0. And second, we evaluate the area of gamma A in the perturbed metric. That is, we calculate the area of gamma A in the with non-trivial m. Finally, we take the difference between the results in 1 and 2. Then we obtain delta SA. In this procedure, delta SA gives the first order correction to the holographic entanglement entropy. For the left-hand side, we have holographic renormalization developed by Balasubramanian Klaus in 1999, and this group, Gustav Skanders, in 1 year later. The TT component of the energy momentum tensor is has a very simple form. Here we can see the mass parameter enters, and the energy of the excited states can be obtained by performing the integration of the TT component over the spatial parts. Now we have the quantities on both sides. And in their paper, they started 2 concrete examples. On the left-hand side, there is a plot of the strip. We fix x1 equals to x with the boundary section length L. And the other x are equipped with the length capital L. On the right-hand side, we have the sphere with the radius small l. These 2 figures are taken from their paper. The entanglement temperature is expressed in this formula. Here, L denotes the size of the subsystem, and C is an order 1 constant. For the simple cases started in their paper, we have very neat expressions for C. For strip, it can be expressed in terms of gamma functions, and it is dependent on D, on the spacetime dimension. For the sphere case, fortunately, we have analytic expressions for the minimal surface, and the result is even simpler than the strip case. Indeed, generically, we can write down this general expression for the entanglement entropy. It's given by constant C divided by L to Z. Here, Z denotes the dynamical exponent of the system. C is a dimensionless constant, which can be fixed by dimensional analysis. Now we have these questions. We know that the first law of thermodynamics always holds, no matter the system is conformal or non-conformal. Then, what will happen for the analog of holographic entanglement entropy in non-conformal systems? From dimensional analysis, we know that C is always dimensionless. But will C be dependent on coupling constants? Sorry.
So the power of the first law of thermodynamics is that the ratio between dE and dS,
yes,
which is the temperature, which is a universal quantity,
yeah.
so independent of the shape and etc.
Yeah.
And but here, if you do a small perturbation, of course, dE will always proportional to dS.
Yes.
And there will be some prefactor. And if that prefactor depends on the shape or depends on the state, etc. And then what's the meaning of this formula?
I'm sorry. Sorry, to my understanding, this is still unclear. Here, what I'm doing is just to show the universal behavior of C. For conformal systems, it's constant. For non-conformal systems, it also exhibits something that is unexpected. And finally, can we give a systematic derivation of the first law-like relation?
Is it positive or no? It's non-positive.
Sorry?
Is it positive, this temperature?
Positive? Yes. It's for sure positive. I will try to answer these questions. Now, before moving to the main result, let me introduce our playground. To study non-conformal systems, we have a novel playground, that is non-conformal DP brains, which was started extensively by these people in 1999. This is the metric written in string frame. Now we can see we have many different coupling constants, string coupling, Yang-Mills coupling, we have the rank of the gauge group, and we have some other constants. We take the decoupling limit. That is, we take the alpha prime tends to 0, but fix the Yang-Mills coupling and the dimensionless radial coordinate fixed. In this limit, gravity decoupled from the branes, and we have the effective metric in the decoupling limit. We can see that here, the Yang-Mills coupling, the rank of the gauge group, still entered the metric, and it may be natural to expect that the results may have some dependence on the Yang-Mills coupling and the rank of the gauge group. This description has its own regime of validity. This regime is obtained by requiring that both the dilaton and the scalar curvature are small enough, which leads to this expression. Here, this quantity denotes the dimensionless effective coupling. Non-conformal D branes always induce very rich structures. Let's take D2 brane for an example. Yeah, this was taken from their paper. In the UV, we have perturbative super Yang-Mills theory. As the effective coupling goes up, we have type 2A D2 branes. And in this region C, we have M3. At their time, they didn't know what it should be. But nowadays, we know that it should be ABGM. And as the coupling increases, we have M2 brane and ADS4. And in the DPIR, we have superconformal field theory. Now, we come to the speculations. As I said, non-conformal DP branes encode very rich structure, and it possesses various coupling constants. So what will happen to the constant C? Is C proportional to the effective coupling? And this seems to be the most natural guess. Or is C a combination of dimensional coupling constants? Or is C independent of any coupling? Before coming to concrete results, let me introduce the nearest extreme counterpart of the DP brane, which is also our starting point. The nearest extreme DP brane can be obtained by simply incorporating the blackening factor Fu. In this background, the dilaton remains the same as the extremal background. And the regime of validity can be obtained in a similar way. But now here, U0, which denotes the position of the horizon, enters. Questions? Okay, let's come to the main results. This is the general setup. Since we are interested in non-conformal branes, we just focus on P equals to 1, 2, 4. Because the non-conformal extremal branes and near extremal branes have the same dilaton. So we can just consider the fluctuations of the metric only. Furthermore, we follow Takayamagi's assumption. We assume that the near extremal background gives the general dual description of low energy excited states. It does not necessarily to be black DP branes. Yeah, we may assume that it can describe some star-like configuration or something else. Furthermore, we assume this relation also following their assumption, which enables us to perform the perturbative expansion. Recall that we are working in 10-dimensional string frame. So the Yu-Takanagi formula receives some modification. This is because the entropy should always be evaluated in Einstein frame. So we have to take this factor into account. Here, this quantity denotes the determinant of the induced metric calculated in string frame. Now let's consider the simplest case, the strip. As I showed in the previous figure, we can easily write down the area functional. It looks a little bit complicated. It has the Yang-Mills coupling. It has the rank of the gauge group. This quantity is also appear here. For the leading order holographic entanglement entropy, please see this paper by Van Niekerk, which appeared in 2011. Following the general steps, we can work out the first order correction to the holographic entanglement entropy. This result also depends on the Yang-Mills coupling. Fortunately, N and DP disappeared. Here, CSA is some complicated number, which is expressed in terms of gamma functions. To calculate the quantity on the left-hand side, we applied the method developed by Robert in 1999, and it's simply given by this expression. We can see that the energy of excitations also contains the Yang-Mills coupling. Finally, we can obtain the entanglement temperature. It is given by C over L. But here, C is a number independent of any gauge couplings. Shall I continue? Okay. Yeah, we just performed the analysis in 10-dimensional string frame. So we may ask, what's the behavior in other frame? Therefore, we consider P plus 2-dimensional effective theory. We carry out the dimensional reduction on the sphere, which results in P plus 2-dimensional Einstein-Dilaton system. This system is equivalent to the dual frame metric in P plus dimensional Einstein frame. I will say something more about the dual frame in the final part. And this is the effective action. We have Einstein-Hilbert term, we have kinetic term of the scalar potential. Here, this term is the standard Gibbons-Hawking term. And these are the explicit expressions for the scalar potential. This theory admits the following solution. Here we have already neglected unimportant numerical factors. We can see that this background is conformal to ADS black hole. In order to show its connections to the higher dimensional origins, in the following I will do a case-by-case analysis. First, let's consider the D1 brane case. As usual, we introduce the Z coordinate, and this is the metric. We can easily obtain the area functional with the function Gz. Then we can perform the calculations step by step, and we work out the first order correction. And for the energy of excited states, Professor Rungad Tsai and Ota developed a method for constructing energy momentum tensor in this background, which conformal to ADS. And this is the result for the energy of excited states. Finally, we obtain the entanglement temperature. And the result is C is still a number which is independent of any gate couplings. For D2 branes, we can perform similar analysis. This is the first order correction. It contains Yang-Mills coupling. It contains the rank of the gate group. And the energy of excited states can be obtained in a similar way. Finally, all these factors cancel. And the entanglement temperature is given by 26. And the C is once again constant, independent of any couplings. For D4 branes, the story is the same. Here comes some remarks. For non-conformal branes, we have shown that the entanglement temperature can be expressed by C divided by the size of the subsystem. Here, C is independent of any gate couplings. We have done the calculations in both 10-dimensional spacetime and in P plus 2-dimensional effective theory, and the behavior is always the case. For the strip case, if we consider D1 branes, we find that the integral in the area functional is the same as that of ADS4, as discussed by Takayamagi's group. This is not surprising, because if we start from M2 branes and we perform the dimensional reduction, we have fundamental string, and then upon S duality, we have D1 branes. On the other hand, the effective theory, the Einstein-Dilaton system, can be embedded into pure Einstein gravity in anti-de Sitter spacetime. Similar situation also holds for D4 branes. That is, we start from M5 and perform the dimensional reduction. We have D4. But the strange thing is D2. For D2 branes, we cannot see explicit connections to ADS. Maybe this illustration is not so proper. D2 brane is also obtained by dimensional reduction of M2 branes, but it's not directly connected to ADS. In this case, C is still independent of the gate couplings. Questions?
Understand why the entropy is always proportional to L squared? So it seems that given that, then this just follows from dimensional analysis.
Yeah.
Then there's no other dimensional parameter can come in.
Yes. Yeah. I agree. But the point here is we have various couplings in the theory.
Right. Yeah, but there must be a simple way you can understand why, for all dimensions, the change in entropy is only proportional to L squared. And if you understand that, then it's guaranteed everything else must cancel.
Yes. But unfortunately, I do not have a deeper understanding on this behavior, so we have to perform a case-by-case calculation. The point is, we want to know if C is dependent of the gate couplings or independent. If we have some quantity C which is dimensionless but dependent on the gate couplings, we have different gate couplings, and we can combine them into a dimensionless constant, and then we may study the evolution of the entangling temperature from the UV to the IR. But in this case, C is always constantly independent of any gate couplings. To be honest, I'm not clear about deeper understanding on this constant behavior.
Trace your calculation, you should be able to see why it's always proportional to L squared. Just from trace your calculational step, then you should be able to see where that L squared comes from. Then you should be able to see why. Yeah, this is something you should be able to see from your calculation.
Thank you. Yeah, for the sphere case, we can write down the area functional, which is still dependent on these couplings. And unfortunately here, the expression is not directly related to the cases in ADS. For the non-conformal branes, we do not have analytic expressions for the minimal surface, so we have to resort to numerics. For D2 branes, we have this number, and finally the entanglement temperature is given by equation 34. We can see that the constant C is of order 1. For D4 branes, the situation is similar, but it has a larger value. Okay, I'm running out of time. So let's come to the summary. We consider the entanglement temperature of non-conformal DP branes. We consider the strip case in 10-dimensional spacetime, as well as the strip and sphere cases in P plus 2-dimensional spacetime. We find that the entanglement temperature is always expressed as C over L. C is a dimensionless constant, but independent of any other dimensionful couplings. The next task is to obtain a complete derivation of the first law-like relation. Before doing that, let me remind you some other paper. This group started the non-conformal examples of Einstein-Maxwell dilaton system, and they obtained the black hole solutions by perturbative method. And in that paper, they found, this is natural, which can be determined by dimensional analysis, but they found that C can be written as the ratio of two dimensionful constants. If we turn on other components of metric fluctuations, the first law-like relation will be modified. We have this additional term, which is related to the pressure. This expression has been obtained by different groups, including Robert. The derivation of the first law-like relation requires the knowledge of holographic renormalization in asymptotically ADS spacetime. But for non-conformal DP branes, the holographic renormalization was carried out by Skanderis and Taylor and their collaborator in 2008. They worked in the so-called dual frame, which is related to the string frame by conformal transformation. And as they argued in this paper, the dual frame should be the correct holographic frame describing the physics of non-conformal DP branes. The effective P plus 2 dimensional theory is given by this action where gamma, beta, and C are constants. So we expect that we may be able to derive a general first law-like relation if we turn on the metric fluctuations of the spatial components. This is still ongoing. Okay, I will stop here. Thank you very much.
In view of the time, just one very quick question.
Right.
So in an actual first law-like process, you imagine a dynamical process where you add energy and you measure heat flow. So what happens if I consider a time-dependent geometry where I collapse matter to form a black hole, and I use the covariant entropy formula instead of the Ryutakinagi formula? Would you get a different answer for this entanglement temperature?
But I'm wondering if we can still define a temperature in time-dependent background.
Well, there's some coefficient, let's say, which probably doesn't depend on time at late times, I would assume. So I'd like to, maybe that coefficient is, is that coefficient the same or not the same?
That's a nice point. But it should be then, maybe something independent.
Okay, I suggest we break for tea. Thanks, Da-Wei.
Thank you.